Welcome to this video on symbolic math in Python. So in this video we will use SymPy to do algebraic operations in Python, for example solving equations, and we will compare how that is in relation to doing numerical solutions, which is what we have been doing so far. So we will import some standard stuff, and then we will import SymPy as SM, and I will also, as a new thing, import this display from IPython to display some stuff later on. So let's consider a consumer problem. So I think a consumer problem where we have got conductors preferences, and we have a constraint which is your budget, your expenses should equal your income. If you want to solve this symbolically in Python, then from the SymPy package you start by defining everything in the equations as symbols. So you say that x1 is a symbol and x2 is a symbol, and you define how the symbol looks in the equations and how we are calling it in Python, and we make those very much alike. So if I run this, then you can see here that x1, for example, here that's now of the type of a core symbol from SymPy. So now we can begin to work with these symbols, and we can simply write out the equations as if they were regular code. So we can say if we want to write the objective, then we just write it out as what it is, and you can see that it renders it nicely as sort of this format here. If you want to write an equation, then you need to sort of use the EQ function in SymPy, and you can sort of define the equation in this way. So this is just an expression, and this down here is an equation. And now we can solve this in 4 steps. We can isolate x2 from the budget constraint. We can then substitute in x2 in our objective. We can take the derivative with respect to x1, and we can solve the first order condition for x1. So if we want to isolate, then we can simply say that we want to solve the budget constraint in terms of x2, and then we get out the solution for x2 here. We could also have done that manually, but now just to show how we can do this symbolically in Python. Then we can substitute in, so we can take our our objective, and then we can substitute in x2 with this expression that we just calculated. So now we have that our objective is still our x1, but now instead of x2 we have this expression for x2 in terms of x1 and the prices and income. Then we can take the derivative. So we take our objective, and then we take the derivative with respect to x1, and then we get some derivative out. And now we can solve this derivative by saying that we take the first order condition and we set it equal to 0, and we solve for x1. And in this way we have now solved our problem symbolically. We all do this using the solve function. You could also use something called solve set, which will be the default in the future in SymPy, but I prefer for now at least to use solve. Okay, I think you should try to do exactly what I've just done, but just doing it with quasi-linear preferences instead. So pause the video and do exactly the same, just with this different objective. Okay, the solution that you should have found is just below here. So now we have a new symbol. So we need to define our gamma, and then we have a new objective, which is now just the square of x1 plus gamma times x2. This might have been a bit tricky to find. You might have done it somewhere else by raising to the power of a half instead. That's also fine. And then we do the same step. We do the substitution. We do the derivative, and we solve the first order condition for x1. Okay, so that's actually fine here. And look, now one thing I did slightly different is I actually didn't write it up as an equation, and I think that's sort of because it assumes here that I actually set it equal to 1. So maybe to be a bit more similar to what I did above. Maybe I should do something like this, and it gives me exactly the same result. This is a bit more explicit. I think I will update the code, so this is how the solution is. Okay, so this is basically how you can do the symbolic solution in Python in these steps and using the various SymPy functions. Once you have that solution, you can do various things with it. You can print it in LaTeX format, so you can get out what is the LaTeX expression of your solution, and you can copy this into a document. But what's also nice is that you can turn it back into a Python function. And this is called sort of you lampify the function. It's the same as the lambda functions we sometimes working with. So to take a simple example of that, if we have some symbol x, then we can say, okay, now let's take the square of x as a function. So we say that the argument to our function is x, and the expression is x raised to the power of 2. And then we can evaluate the function of this of the value 12. So now we can see that we sort of this x squared, that's just a NumPy function, a Python function as anything else, and we can put in a number and we get out our result. We can do this a bit more complicated as well by using our solution. So we can say, let's create a function which is based on our solution to the consumer problem, but for use with NumPy and Python numerical stuff in the same way. So we call the lampify function from SymPy. We say that our arguments, that is our price of the first good, our income, and our preference parameters. And then we use our expression as that's the solution that we got. Then we put in some values. We take a vector of the prices, we take a value of the income, and we take some values of the preference parameters. And then we can now simply call the solution function as we had before, and we can print out what the demand is. So in this way, we can sort of start by doing some symbolic stuff, but then we can do some numerical evaluations afterwards, which is often nice. I think you should try to do the same thing with the solution you found for the quasi-linear preferences numerically, but now do it numerically and set gamma equal to 1/2, P1 equal to 2, and P2 equal to 1, and an income of 10. So let's pause the video and do that now. The solution is written here. I just write up the values of these different things, and then I do the lampifying of the solution that I found before, the sol_alt, and then I find the demand and I print out the demand. Okay. A third thing you can do is you can sort of analyze analytical properties of the solution of any expression in general. So we can ask, is demand always positive? And the way you can do this is you start by making assumptions on the inputs. So we say here that for all the variables in our prices and in our preferences and in our income, we sort of make the global assumptions that this is a positive variable. So now I sort of print out our set of global assumptions, and this is sort of saying that this is a real number and it's positive, 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 positive. And then we can ask the computer a question. So we can ask, is our solution a real positive number? And we can say that it answers true. If we now sort of remove our assumption that P1 here is positive, then it cannot answer anything, because then it doesn't know if the solution is if the solution is positive. But it does know if we do do it up here. Sometimes it's very clever in answering these questions. Sometimes it's a bit harder to get it to the right answer. But this can be useful. We can also clear all assumptions by simply writing it in this way. Okay, you can do many other things with symbolic math in Python. So here I just define a symbol, and I can now take a second order derivative. This is just sort of taking it as an expression, and then I can also evaluate it. or I can actually take it using diff instead of derivative. Then it takes the derivative, or I can take the derivative and I can say do it, and then it sort of takes the derivative and find it in this way. I can also do it with two variables, and you can sort of take a derivative of that. I can take integrals, and I can evaluate those integrals as well if I actually do the integrate function of it. I can take limits of functions. Here I want to take a limit of the CRA function when rho goes equal to 1 from goes towards 1, and then you can sort of find out that this limit is actually the logarithm. You can also do integer math here, where you have 7 by 3 and 3 times 8, and you can now yes, here I'm using the display to show how that is, and then I can compute some expression here which now sort of keeps everything in integers, so you can sort of use it in that way to do fully precise calculations. You can also, once you have this expression, you can ask it. You can ask it to simplify. Now here, for example, I take the sine function and square it plus the cos function and square it, and if I simplify this relationship, then you can actually know that this is always equal to 1. So you can sort of simplify expression in this way. You can also solve multiple equations at once. So if I define my symbols, if I define 2 equations, and that looks like this, then I can simply ask it to solve this system of equations here. And here it finds all of the solutions that are to this equation. And so here there is 4 different solutions. Okay, and there's many more stuff you can do. Look up in the documentation for finding that. Okay, let's compare a bit about how numerical and symbolic solutions are. So if we think about a function which is x squared minus 1, then if we want to sort of find out where this function is equal to 0, then we might run into a couple of problems. We could find that there will only be convergence to one root. We could find that conversion will not be exact, or we can find that it's hard to converge at all. So let's illustrate this numerically here. So I loop through various values of x0, so that will be my guess. Then I will do a root finding, where I will use this function up here. So I will try to find a root in this function, and I will do that using this initial guess, and then I will print what is the implied result, and was the solution a success or not. And you can see that depending on the initial guess here, I can either converge to -1 almost precisely, or -1 with a small difference, or I can converge to 1, or 1 with a small difference. And success can either be true, or it can actually also be false if I start at a bad guess here 0. So this is the problem of doing numerical solutions. You can run into problems like these things. And here symbolic stuff is nice, because here I just say I want to find all solutions to this equation here, where there are some things that are presenting it equal to 0, and we find exactly that it's -1 and 1. So that's the good thing about doing symbolic stuff. As soon as stuff gets more complicated, it's very hard to use the symbolic stuff, and you have to use the numerical stuff. So I think that too many students spend too much time on using this symbolic math in Python. You should focus on the numerical stuff. That's where it's really powerful and scalable in terms of big problems. But it is nice sometimes to be able to do stuff like this. This was the main part of the video. Sort of the final section here is is sort of an example of why you can do something that's a bit more complicated symbolically. You can actually also solve matrix equations symbolically. So that is equations on the form AX equal to B. And I will not go through this in detail, but there is a function here which creates a SymPy matrix sort of from information on where the positive where there are elements in it, all the non-zero elements in it. And then there's a function for filling out the matrix based on a numerical matrix. And just to show how that works, then sort of you can construct a SymPy matrix that has these non-zero elements 1 1 1 2 2 1 2 2 3 2 and 3 3, and then there's zeros on the non-mentioned places. Then you can sort of, with this matrix, you can do for example find the inverse of it, but you can also put in numerical values. You can fill it out with the numerical values, and you can find the solution in that way just by multiplying with it. So that's just to say you can do something that's a bit more complicated as well. By the way, you sort of, if you take the determinant of the symbolic matrix and you multiply the inverse with this determinant and simplify, then you get an expression that's much nicer looking than what we got up here. Okay, but this is sort of an extra thing that you can do. This was all for this video.